First of all, I would like to start by thanking the organizers for giving me the opportunity of being here today to present recent experiments that we have been doing in my group at ICFO in Barcelona. So what we study in my group are Bose-Einstein condensates that we dress with light. And what I want to show you today is that by doing that, we can make our system become chiral, that is different from its mirror image, and that when this chirality affects the interactions between the particles of the BEC, we can make our system realize a special type of gauge theory, a topological gauge theory. So now my talk is going to be a story about Bose-Einstein condensates that we subject to artificial gauge fields. That means to a synthetic vector potential that acts on the atoms and from which we can derive an artificial electric or magnetic field. But unlike many experiments that have been done over the years on these systems, we are not going to subject the quantum particles of our BEC to classical gauge fields, but instead we want to go a step beyond and make these gauge fields quantum. So what we actually want to do is to make that this vector potential becomes a quantum mechanical operator that acts onto the matter field, and also to have back action of matter into the gauge field. So we need to engineer a proper theory for quantum gauge fields coupled to quantum matter fields. So better we take the good quantum theory of fields, and this is gauge theory. So we already heard in the previous talk that gauge theories are very fundamental for our understanding of nature. They describe interactions between elementary particles as mediated by gauge bosons. Also, they describe gravitational physics because general relativity is a gauge theory. And if we go to low energy physics, also gauge theories appear as effective descriptions of certain strongly correlated materials like spin liquids, spin ice, or fractional quantum Hall states. And even in quantum information science, if you think of Kitaev story code and error correcting codes, Kitaev story code is nothing else than a Z2 lattice gauge theory. So it seems that if we could get our Bose-Einstein condensates speak this language of gauge theories, we could greatly expand the scope of problems that we can tackle by quantum simulation. And this is really what motivates us to open these quantum field theory books to figure out what are the ingredients that we need to engineer in the lab to make our cold atoms realize a gauge theory. And we can do that starting from the simplest gauge theory that we all know about, which is quantum electrodynamics, and we see that we actually just need 3 ingredients. First of all, we need to have a system with matter and gauge degrees of freedom. For QED, we need to have electrons and photons. Then these gauge fields need to be minimally coupled. That means that the kinetic part of the Hamiltonian, we need to replace the momentum operator by P minus A. And then finally, we need to have a system that conserves the electric charge. And this implies that the gauge theory is gauge invariant and reflects into the fact that in every point of space and time, these gauge fields need to obey a local conservation law that links them to the matter fields. And for QED, it's nothing else than Gauss' law. So we need to have that the divergence of the electric field is equal to the matter density. We heard in Monica's talk that this is not so easy to implement in the lab because it leads to very constrained dynamics between these matter and gauge fields. However, I think it's really nice to see that over the last years, more experiments have been doing a lot of progress in this direction. So the first experiment started by just implementing key ingredients, then moved to building blocks, and now we have complete implementations of gauge theories. And all experiments that have been done until now realize a discretized version, a lattice version of QED in 1 + 1 dimension, so 1 spatial dimension, 1 temporal dimension that Monica talked about. That's the Schwinger model that can be done with trapped ions, with arrays of Rydberg atoms, and also with neutral atoms in optical lattices. And it's a pity that you cannot hear in the next talk the beautiful experiments that have been done in the PAN group on this topic, but I very much invite you to read these papers to learn more about these experiments. So now we know how to implement the Schwinger model, and the big challenge in the field is to scale these experiments further because we want to move to implementations of QED in 2 dimensions or in 3 dimensions. And also, why should we stay in page 1 of the volume 1 of the book? We can also be brave and tackle more complicated gauge theories. And in my group, what we got interested in is in a special type of gauge theories called topological gauge theories that appear in the description of quantum many-body systems, and the most famous of these gauge theories is called the Chern-Simons theory, that in many aspects looks very similar to QED. You still have matter and gauge degrees of freedom minimally coupled, but that has a different conservation law, which is called flux attachment. So not anymore Gauss law, but this relation between the magnetic field and the matter density. So to understand what this Chern-Simons gauge theory is about, the best is to look at a physical example. So let's look at the fractional quantum Hall effect, which is a physical effect that is described by this gauge theory. So the fractional quantum Hall effect appears in systems of quantum particles that are subjected to a strong magnetic field and confined to a 2D plane. And we know that for certain Philip fractions, we can have fractional quantum Hall states that appear, which are very interested many-body strongly correlated states, which have, for example, excitations that have charge that has fractional values, and also these excitations, if you take two of them and you exchange them, they don't behave like bosons or fermions, so they don't pick up an exchange phase for the wave function that is 0 or pi, but they can take any phase in between, so they are anyons. Now, there is a lot of effort put into understanding better these strongly correlated states, and you will hear tomorrow in Marcus Greiner's talk the approach of quantum simulating it with bosonic atoms in an optical lattice and subjected to a strong magnetic field. But in my talk, I want to take a very different perspective and just think whether we can build an effective single particle picture that would allow us to get an intuition on this complicated system. And this is, of course, not an idea that I got. This is an idea that Wilczek already proposed when we introduced the concept of anyons, and that builds on the concept of flux attachment. And what is flux attachment? It actually consists on taking the particles of the original strongly interacting system and replacing them by new particles, these orange particles here, which are now weakly interacting. But you put all the effect of the strong correlations into the fact that these particles grab part of the external magnetic field with them. Yeah? So they form some composite objects that are made by these particles, and these solenoids here, these flux tubes, attached to them. And now, if you think in terms of these composite particles, fractional quantum Hall physics becomes pretty simple, because, for example, this anyonic exchange phase, it just comes from the fact that if you exchange two composites, you're exchanging two solenoids, and then you have an Aharonov-Bohm phase associated to that. So in this type of model, what is a very important quantity, of course, is the magnetic field that is created by all these flux tubes. And this magnetic field is proportional to the matter density, since these flux tubes are glued to these orange particles. So this is why this relation that I told you about before is called flux attachment, and it's actually the local conservation law of a theory which describes how these orange particles interact with the gauge field that gives rise to this magnetic field, which is nothing else than Chern-Simons gauge theory. And this theory, as I said before, it's very similar to QED, so you have matter that is minimally coupled to the gauge field, but the gauge field is very special, because it cannot propagate when matter is not there. So you can think of it as photons that are very, very heavy. They have a very large mass. So they move, but only when matter moves. They always follow matter. So then you could also think, well, if I now set matter to 0, then this gauge field is going to become totally trivial. This is actually not always the case. You can have non-trivial solutions in vacuum depending on the topology of the space, and that's precisely why this type of gauge theories are called topological gauge theories. Now, if you could engineer Chern-Simons theory in the lab, then you could get anyonic behavior without the need for strong correlations. And this is actually an old hope from condensed matter people. So there are proposals that keep coming around of how could one engineer a condensed matter system that would have anyons without strong interactions. My favorite proposal is actually Canadian. It's from quite some years ago, but to my knowledge, no one has managed to do that experimentally. So we want to have a try at that with cold atoms. And actually, to be honest, engineering Chern-Simons theory is still a bit too hard for us. So what we focused on is on implementing the reduction of Chern-Simons theory in 1+1 dimension, which is called the chiral BF theory. So you can think of this theory as the Schwinger model of this topological gauge theory. So basically the simplest model that already has all the ingredients of these types of theories and from which you can hope to scale up. Yeah? And this is actually a very interesting theory on its own, because it's the effective field theory that describes the edge of a fractional quantum Hall system, and it has excitations that are matter wave packets that can propagate without dispersion only when they move in one direction, but that disperse when they move in the opposite one, and which are nothing else than the many-body analog of the chiral edge states that you see in integral quantum Hall systems. So with this long introduction, I come to the outline of my talk. So actually, first, I want to introduce you a little bit more what this chiral BF theory is about and how we can encode it in Raman-coupled Bose-Einstein condensates. And then I will move you to the experiments that we do with these chiral Bose-Einstein condensates in the lab and how we can study their interesting properties. So let's start with the chiral BF theory. So the chiral BF theory is the theory that you get if you take 2D Chern-Simons theory, and as I said, you reduce it to one dimension, so you focus on the edge of the system. And this is a theory that was introduced in the 90s by Silvio Rabello, and then subsequently studied in much more detail by Roman Jakif and collaborators. And while in the original theory, you have a matter field and a gauge field that has 3 components, temporal and the 2 spatial components, when we do this dimensional reduction, then the Y component is gone, and what you get is an extra field that is a scalar bosonic field. Now, the Lagrangian of this theory, I have written it here. It might look a bit complicated, so let me guide you through it. So the first term of this Lagrangian is a pure gauge field term. It couples the scalar field B to F, which is the electromagnetic field tensor, and this is actually what gives the name of the theory, because it reads just BF. And then this theory is called chiral. This comes from the second scalar field term, which actually involves only this B scalar field, and it's a term that you add phenomenologically after doing this dimensional reduction in order to have your effective field theory that is chiral and that reproduces the behavior of the edge of the original system. And then the following 2 terms are quite easy to understand because it's just minimal coupling of the matter field with the gauge field, and then this matter field in the original models is taken to be bosonic, so it has its own interactions that depend on the matter density. This is this term here. So now when you see this Lagrangian, and you're an experimentalist like me, you get scared because you really don't see how to do this in the lab. However, you can open the book and figure out what the local conservation laws of this theory are, and they actually link this B boson and the electric field to the atomic density, and then you can use these local conservation laws to get rid of all the scalar fields and gauge fields that are in this expression and put everything in terms of the matter density that is going to greatly simplify your model. So this procedure is actually called technically encoding in matter-only degrees of freedom, and it's a trick that we learn from the trapped ion experiments. That's actually what the trapped ion experiments do to engineer the Schwinger model. So if you use this trick, you remove all gauge fields, but there is a price to pay, which is that you get some new interaction term between your matter fields. And for the Schwinger model, if you use Gauss' law to remove the gauge field, the interactions that you get are, not surprisingly, Coulomb interactions. But if you do that for our chiral BF theory, then you get a very weird interaction term that you're certainly not used to, which actually reads the current operator for the matter density times the density. And this term, Roman Jakif called that a chiral interaction term. So why is that? Because if you think of a semi-classical matter wave packet, you know that the current operator is nothing else than the velocity of the wave packet times the density, so h per k over m times density. And now if you replace in this expression at the semi-classical level, what you are going to get is an interaction term that scales with density squared, so these are just contact interactions, but now we have an interaction strength that depends on the center of mass momentum of the wave packet. And this is actually a pretty weird interaction term, so you will have a system that has different interactions depending on the momentum of the system, and that can be different when the atoms move in one direction or in the opposite direction, and you see immediately that this is an interaction term that explicitly breaks Galilean invariance. It explicitly depends on the velocity of the particles. So how can we make this interaction term? Actually, we can do that if we use a 2-component Bose-Einstein condensate with 2 internal states that I will call in the rest of my talk spin up or spin down, or blue and green atoms, and you couple these 2 states with 2 photon Raman transitions. Now, if you look at the dispersion relation of these two states in the absence of the Raman coupling in the rotating frame, you get the following. So you get two parabolas that are separated by 2 times the momentum of the Raman lasers. This is because in order to go from the spin-up state to the spin-down state, you need to absorb a photon from one laser beam and re-emit in the other one, so you get a 2 kr momentum kick. But now when we put the coupling between the two states, what happens is that we go to the dress state picture, so we get some new atom-photon dress states that I depict here, and if the coupling is big enough, then these states, they just get new parabolic dispersion relation, and the only particularity that they have is that their spin composition, so their polarization, becomes momentum dependent. And this I have encoded in the color scale here of these curves. Now, how are we going to use this for engineering the chiral BF theory? It's actually very simple. The only thing that we need to add to this single particle picture are interparticle interactions, so interactions between the atoms in spin up, which are given by this interaction strength G up, or between atoms in spin down with G down, and make these interaction strengths very different. And this is actually an idea that the group of Patrick Aubert had theoretically almost 10 years ago. Now, why does this work? Because now if you look at these dressed states, but you look at how the atoms in these dressed states interact, you see that actually these coupling constants are different, so the effective interactions of the atoms are going to depend on polarization. This is something that in my group we studied recently for radio frequency coupling. But if now you have Raman coupling, you have in addition that the polarization of the state depends on momentum. That means that if you go to large negative momentum, then you are going to be mostly in the up state, so the atoms are going to interact with this G up interaction strength. If you go to large positive momentum, then the atoms are going to interact with G down interaction strength, and then in between, they will get an interaction strength that interpolates smoothly between the two limits, and you see that in the central region, it's in very good approximation linear, and that's how you can engineer the chiral interactions that you want. And this gives you exactly the chiral interaction term that you need, and you can even adjust the slope of this curve just by choosing wisely these two initial interaction strengths. Now, this is of course a hand-wavy picture, but we can do things formally correctly and then write a quantum Hamiltonian for the system truncated to this lower dress state, and this is what we get. And this is exactly what we wanted, because it's exactly the Hamiltonian for the chiral BF theory at the quantum level, and you recognize here this chiral interaction term that I was talking about before. So now that we know how we can engineer this chiral BF theory in the lab, then let's go there and just make it with atoms and lasers. So what we use in my group to make these experiments is a Bose-Einstein condensate of potassium-39 atoms, and we like potassium-39 because it's an atom that has a lot of Feshbach resonances and therefore widely tunable interactions, and we are going to tune these tunable interactions of potassium-39 to turn them into the chiral interactions that we want. For that, we take potassium-39 in the two lowest spin states, which are these two ones here, at a magnetic field of around 385 Gauss, where you see we have exactly what we need, because we have the green atoms which are on the flank of a Feshbach resonance, so we can adjust their scattering length in a broad range. While the up atoms, they have a very, very tiny scattering length that can be slightly positive or slightly negative, and also the interaction between the two spin components, it's very small. So in our experiments, what we do is that we prepare a potassium-39 BEC here. We subject it to counter-propagating Raman beams with orthogonal polarizations. These Raman coupling beams, we actually choose them at the tune-out wavelength of potassium, such that they only do Raman coupling and they don't add additional scalar potentials. You saw that the chiral BF theory, it's a 1D theory, so we want to tightly confine our atoms such that the dynamics happens in one dimension. This we do with this optical waveguide beam. And then we have coils to adjust the strength of the interactions using the Feshbach resonances, and a high numerical aperture lens here to do in situ imaging of the cloud after letting it evolve in this one-dimensional waveguide. So all our experiments start by making a Bose-Einstein condensate and adiabatically loading the Raman dress states. And once we have done that, what we want is to prepare systems with different center of mass momentum to see this chirality of the interactions. And in order to do that, we add an additional pair of beams to our experiment that we use to make Bragg transitions that can kick our atoms either to the right or to the left, depending on the frequency difference that we choose between them. And then afterwards, we just let the atoms expand in the waveguide, so we remove any longitudinal confining potential and just take an image after different evolution times in this waveguide. Now, this is what you get when you do the experiment, and you immediately see in these images that when you kick the atoms to the right, you get a very different behavior than when you kick them to the left, because while in the first case, the atoms start to expand in this waveguide, in the second one, you don't observe any dispersion at all. And this is even more spectacular if you look at the longitudinal width of the cloud, where you can really see that the kicking right and kicking left situations are completely different. Yeah? So your system is chiral, because the two propagation directions are different, and now you may wonder, what is this chirality about? Actually, this chirality is in the interactions between the particles, because when we kick the atoms to the right, they have effectively repulsive interactions. That's what makes the cloud expand, while when we kick them to the left, they have effectively attractive interactions. And another thing that you see in this plot is that actually the size when you kick atoms to the left does not evolve at all. This is because we are forming a bright soliton, so a matter wave packet that remains self-bound because you have attractive interparticle interactions that hold the atoms together, and then you have quantum pressure that stabilize the system against collapse. So in my group, we like very much self-bound states and solitons. We have been doing several types of them. So we decided that now that we made this new type of soliton, we should characterize it to know more about it. And we came up with an idea of experiment, which was to build a wall for this bright soliton that we have launched to the left. And of course, it's not a wall, it's a blue detune laser beam that we focus to the side of the cloud, and we choose the power to be high enough that the barrier is so high that the atoms cannot tunnel through it, so they are going just to get reflected from it. And then we launch our Raman-dressed solitons against its wall, and what we find is the following. We find that while the system remains a soliton while it moves to the left, when it gets reflected off the wall, it actually starts to expand, so the soliton disappears. So when you see that, if you are an experimentalist, you should be critical with yourself and wonder whether something weird is happening in this barrier. So we decided to run a sanity check. And what we did was to create a soliton with atoms in one single spin component by changing a little bit the magnetic field to a regime where we have effectively attractive interactions in the spin component. And then we launch it against exactly the same barrier. And what we see for a standard soliton is that when it comes to the barrier, it compresses a bit, and then it bounces off, and it remains a soliton. While the Raman-dressed system behaves completely differently because this soliton behavior is only observed in one direction. And then we conclude that actually what we are seeing are chiral solitons, and then we can compare actually the properties of the self-bound states here to what we expect from our chiral BF theory, and we can really conclude that what we are seeing are the chiral solitons of the chiral BF theory. So solitons that can only exist when they propagate to the left but not to the right. And now, to conclude my talk, I also want to address another point, because I started my talk telling you, well, we are going to make quantum gauge fields for quantum particles, so maybe you're a bit disappointed that I never showed you here what the chiral BF gauge field is. And actually, we did this trick of removing the gauge field and putting everything into the interactions between the particles, so you could think that now we are lost, we cannot get information about this gauge field. But thankfully enough, this is not true, and there is a trick that you can use that we learned from the trapped ion experiments, which is that you can use the local conservation law again that gives you the relation between the electric field and the matter density, and by doing measurements on the matter density, then you can reconstruct what the electric field is. And this is exactly what they do in the Schwinger model experiments to get their electric fields. Now what you see in this expression is that when you are going to change the matter density, then an electric field is going to appear, and this electric field is going to be self-generated by the system itself. It comes from the change in density, so we want to see that in the experiment. And we can do that actually by changing dramatically the density of the cloud by making it expand. So now we run a last series of experiments where we take our Raman dress system and we don't kick it anymore, we just release it from the trap into the waveguide, and what we see is the following. So we see that while the system initially has an isotropic shape, when it starts to expand, it actually develops a very weird shape, like a tail to one of the sides. And you certainly already can see it in these images, but if you just take integrated density profiles and do a fit of them, this is what you get, where you can even more clearly see this tail to the right. So what is happening here? Why do we get this asymmetric density distribution? Actually, microscopically, what is happening, we understand it very well. We put all the atoms in a dress state of spin up and spin down, and now when we let them expand, the green atoms will move to one side and the blue to the other side, but they have different interaction strengths, and that's going to skew the density distribution because these green atoms, they have more energy to release during the expansion. But if we just think in terms of the dress particles, we can think of what is happening in terms of electric fields. So what is happening is that the density, when we do the expansion, drops in the center of the cloud, but needs to increase in the edges. This is going to give rise to electric forces that point in opposite direction in the center and in the edges. And also, the forces in the edges, they are not identical because the density does not drop in the same way. And then what you get at the end, it's a very complicated distribution of forces that is going to skew your cloud, and that's what is going to make it asymmetric. So actually, having an asymmetric form of the cloud after their expansion is telling you that you have this self-generated electric field. So we can just characterize the asymmetry of our cloud using the skewness parameter, and this is what we get. So we see that upon expansion, the cloud develops an asymmetry, and this is in qualitative agreement with our theory model, and is telling us that we are generating this chiral BF electric field with the expansion. And with this, I really want to come to the conclusion of my talk. So I told you how we can quantum simulate a particular type of gauge theories, topological gauge theories. We are not yet able to engineer Chern-Simons theory, but we can already do the dimensional reduction of it, the chiral BF theory, and we can do that by engineering a system with chiral effective interactions in a Raman-coupled Bose-Einstein condensate and see the main properties of this theory, which are the existence of chiral soliton solutions for the matter field and of a self-generated electric field when the density of the gas changes. And now this opens many interesting directions in which we can go in the future. So I told you our motivation to look at this Chern-Simons theory is that this is a gauge theory for anyons. Actually, in one dimension, you don't have true anyons, but you have what are called linear anyons. So these are matter fields that have anomalous commutation relations. And we know that this chiral BF theory is a theory for linear anyons. So we are thinking how we could probe that in the experiment. Then, second, I showed you that we can see these self-generated electric fields. But once you have one thing, you always get greedy and you want more. So you would wonder, can we create self-generated magnetic fields? So initially, we thought we cannot, because if you have a 1D system, you don't have perpendicular directions, so how are you going to compute a curl? But actually, there is a way out, which is if you make your 1D system a ring, because then you can have a magnetic field that pierces the ring, and you will see manifestations on it. And actually, there are nice theoretical proposals that you will get a density-dependent magnetic field that will be self-generated by the system itself and will give rise to persistent currents in this ring that depend on the matter density. And we have also been studying this system in a bit more detail and realized that it's also very interesting because it allows you to get information about the topological character of these gauge theories. And we even have an idea for an experimental implementation. Instead of using counter-propagating Raman beams, now we can use Raman beams that transfer angular momentum to the cloud, and they are going to exactly make this model. And then, of course, our long-term prospect is to put together all these ingredients to engineer Chern-Simons theory. There is already a theoretical proposal on how one could do that using angular momentum beams, but this is something that, of course, we need to look more in detail at. And with this, I want to finish by thanking my group that did all these beautiful experiments. So these are people in my potassium lab, 2 PhD students, Annika and Craig, and 2 postdocs, Eletra and Ramon. Now, Annika just defended her thesis, and Eletra moved back to Italy, so we have open PhD and postdoc positions in this experiment, if you're interested. And Ramon is attending the conference, so if you want to know experimental details on what I presented today, and also what we are doing now in the lab on supersolidity in these Raman-coupled BECs of potassium, you should ask him. He had a poster yesterday. All this work has been done in collaboration with the theory group of Alessio Celli at the Autonomous University of Barcelona, and all these new ideas and prospects that we are looking at, they have been done in collaboration with his team members. And in my group, there is a second lab, that's the strontium lab, where we are building a strontium quantum gas microscope. So if you are interested, you can ask me, because Vasily, the postdoc that works on this experiment, unfortunately did not get his visa, so he could not come to ICAP. So with this, I want to thank you for your attention, and I will be happy to answer your questions.
Thank you very much for a lovely talk. Randy?
Hi, beautiful experiment. So if you bounce the soliton off a mirror twice, does it become a bright soliton again?
Okay, that's a very good question that I get many times. I think the tricky thing is that it needs to refocus again. Yeah, so the matter would need to come back again together. So I think what we would get is a train of solitons, because the density would drop while it goes backwards, and then when it reaches the other barrier, we will get smaller solitons coming. But I have to say, we never did the experiment. So maybe we should try.
We'll go there and then.
Hi, thanks for the talk. I wonder, in the most important experiment result plot, so the ladder shape or the pyramid shape. So I wonder, so the y-axis is a time and x-axis is a space.
Yes.
I think that's labels. And my question is, why at some time there's a missing of, like there's no image at all?
Okay, actually here it's a collage of several images. So you rather have to think that each of these images is an experiment, yeah? And then, okay, I think we put the axis right, but you should rather check the paper if you want to see it well. We just took images every millisecond or so, so we just have a time lapse, basically.
So there's like a slit of a time integrated image.
So here, I mean, we just make a system and let it evolve for one time, then we repeat the experiment with another time, and take another image and so on. So these are really like separate experiments, and we see how the system evolves, but over different repetitions of the experiment.
So from this plot, it seems that there is some time that no molecule exists, sorry, no atom exists in the system.
Well, it's just because we did not measure there, because we did not measure for every possible time.
Oh.
So we just measure at time intervals.
I see. Cool. Thank you.
Bill, please.
Maybe you could go back to the original, the earlier picture that shows things going to the right and to the left. Right. Okay, great. Now, okay, now, actually, I was kind of wondering how you got these things. Each one is a fully destructive measurement. It's just that the seams between the pictures was not so evident, so it looked like you were doing this thing with repeated non-destructive measurements, but that's not the case. Okay, so what I really wanted to ask about was the guide. Now let's see, what's the scale? 20, I'm trying to see the distance scale. Well, 20 microns is what on there? I'm not quite seeing, I see the 20 micron, but I don't see how big it is.
Sorry.
There, okay, great. Now what's the Rayleigh range of your guide?
So this is way, way longer. It's like centimeters,
okay,
because we have a not very focused.
Right, so that means it's not very tightly focused. So it's not really 1D.
No.
So what I'm wondering is, what effect does that have, if any, the fact that it's not really 1D?
Okay, so the system is, let's say, kinematically 1D for these dynamics, because we go to fairly small interaction strengths, yeah? But it's not really 1D, as you say. And what this has as an effect for the chiral soliton experiments, I think none, because we really have no transverse dynamics. Of course, we need to stay above the soliton collapse threshold. When the system would realize that it's 3D, it would collapse, so we put ourselves above of that. In the repulsive regime, we start to see a bit of transverse dynamics happening in the waveguide sometimes.
Yeah. Now, when I look at the left one, the one with no dispersion, it looks like there's also something else going on, actually even more than what I see in the right, where everything looks relatively smooth. So I'm wondering, is that just the extra transverse dynamics that isn't included in?
So what we have here in
thinking?
this experiment is mostly that we have particle loss, because there is photon scattering from the Raman beams, and there is also three-body losses, and this reduces the atom number, and this reduction in atom number, because there is also three-body loss, is bigger when we go to the attractive regime than when we go to the repulsive regime.
Now, the thing about a soliton, bright or dark, is that I mean, you need specific conditions. So what I'm wondering is, when you start off going to, kicking it to the left, does the stuff that's not soliton, does that go off in some other way? How does that sort out?
So this is a good question. Of course, what we have to do is to reduce the initial atom number before the kicking to make sure that we would not have a soliton that would collapse because it has too many atoms. Yeah. So this we have to pay attention to. And then, I have to say, we also did numerical simulations, and what the experiment does is essentially what the numerical says. So it goes, we quench it to the attractive regime, and then it compresses a bit, and then it seems to remain kind of unchanged. Then when you reach the barrier, there is, on the numerics, beautiful dynamics and interference and so on, but of course these are things we cannot see in the experiment.
I see. So the stuff, it sort of forms itself into the soliton that it wants to be without losing a bunch of stuff.
If you choose well your
choose
trap
well
and
the
your
initial
parameters
conditions.
and
Okay.
so on. Exactly. I have very good students that found the magic knobs, and then it works very reliably.
Okay. Well, what if you don't choose it? What happens then?
Well, I don't know. There are all sorts of bad things that can happen in the experiment, but I think they would be the best people to say, because they are the ones that adjusted it.
Okay.
Okay. Thank you for the lovely conversation and for a great talk.